Do today is move to a new chapter. Okay, we have done with statistical inference on the mean of a distribution. Right? We try to estimate the mean of a distribution using confidence interval. Right? We also learn how to do hypothesis testing related to the mean of a distribution. Okay, and that's a univariate study. We try to study one population and try to study its mean, because mean usually is a number that people use to represent that. All right, or to understand the distribution, which is the center of the distribution. Right? A lot of times people, if you have two different populations, people will compare the mean of two populations to understand the difference and so forth. Right? So, but what if sometime people like to study two variables? And that happens all the time. That's always, right? At least two variables that we are studying. We're trying to understand whether this particular factor affecting that behavior, right? This particular medicine will really help improve the blood pressure, right, or lower cholesterol level. Okay, so there's always like one is like an outcome, and one is some factor, right, that affecting the outcome. So a lot of times people like to examine the correlation between these variables. Okay. Today, what we're going to look at is first this type of relation, the relationship between two quantitative variables. Both variables are quantitative. Earlier in this course, we learned how to display the two quantitative variables jointly by using a scatter plot. So we can see whether there's a trend, right? Clear trend, clear pattern between the two variables. Right? And then we can understand the significance between the correlation between two variables. And you look at this example too, right? We were trying to actually, this is a linear relation, right? Just kind of review the idea of linear relation. What is linear relation? Linear means straight line, okay? When you talk about relation between two variables and find out that the relation is a straight line pattern, we call it, that relation is linear relation. And this particular relation is deterministic, all right, relation that, you know, whenever you have an input value or a value for x variable, there is a specific y value correspond to it. Right? For instance, I'm going to a drugstore. It'll cost me $3 to get in there, right? And then I'm buying some Tylenol, right? Each bottle is $2. So I can come up with this relation between the price, a cost, right, for buying X bottle of Tylenol, for instance, for going to this drugstore. You go in there, you have to pay $3. And then for each bottle you buy, it's $2. So if I buy one, it's 3 plus 2. That's 5. Right? If I buy 2, that's 3 plus 2 times 2 would be 7. Okay? If you buy 3, 2 times 3 is 6 plus 3 is 9. Okay? And it keeps going. If you try to plot these, all these possible x and pairs of x and y value for each number of, a different number of bottles you buy, you're going to find out that that relation is kind of a straight line relation, right? All these dots follow on the line. Okay, and that is called deterministic model because every time you have an x value that is fixed, the outcome value always be another fixed number. If you buy one bottle, it's always pay $5. Okay, for coming to this particular store, always. Okay, however, in practice in the world, there are some relation that are not so deterministic. Okay, if you recall this example, we talked about number of handgun register and number of people killed in the community or in certain states. Okay, in some years you may have 13 people, 447,000 people handgun register, but there are 13 people killed. Right. In another year, you might still have the same number of handgun registered, but number of people killed will be different. Okay, so the relation between the outcome and the factor, or the x and y variable, they are not fixed. It varies even at the same level of x. Right, the y may be different. Okay, and when we have situation like that, we still want to model the trend, right, and try to have when there is a specific x value there, you want to be able to find out what y value is, and that's typical. That's a lot of time what we like to do, and that's a lot of time why we need to collect these data. Right? So we collect these more than 10 years of data. Hopefully later on, if this particular year handgun registration is 500,000, I'll be able to know about how many people got killed. Okay, and how do we come up with a formula to help us to solve a problem like this? The outcome is not deterministic. Well, there's a so-called regression approach that we can take. Right? But before we get into that, let's look at these terms, review these terms. In this particular problem, we're interested in modeling how many people got killed. Number of people got killed. Why are they getting killed? Well, because of so many factors. Okay? And this is the outcome. So many people got killed is the outcome for maybe some phenomenon or certain factor that's affecting it. So we call this number of people killed the outcome variable or response variable, right? In response to certain level of factor, okay, and a certain level for a certain factor that is affecting it. And then number of handgun register, we believe this is a factor. This is affecting, right, why that many people killed. So we call this variable explanatory variable. Sometimes people call it factor variable. Sometimes people call it predictor variable because you can use that to predict usually how many people get killed. Okay, so there's several names for this. And we've gone through this in the beginning of the class. All right, so hopefully you remember these two terms. What is response variable? That's outcome variable. What is explanatory variable? That's a factor variable that's affecting these response or affecting these outcomes. And usually when we have these pairs of number, okay, we can make a scatter plot if you recall. Okay, this year we have 447,000 and have 13 people killed. We plot that number, okay, and it's somewhere here. The horizontal axis is number of handgun register, and vertical axis is number of people got killed. And usually when people making these so-called scatter plot, the vertical axis is for the outcome variable. Horizontal axis is for the predictor variable or explanatory variable. Right? So we can keep plotting all these points, and we get these scatter of dots on the chart, right? And it helps us understand the trend. If you see these trends, it seems like as number of handgun register increase, number of people got killed increase, right? And we call this relation a positive relation. We mentioned that earlier in the course too when we explained this. Right? I didn't want her to explain it again. Right? As number of handgun register increase, number of people got killed increase. This is called positive correlation. Okay. If you try to use a line to explain this correlation, that line going to go like this, right? And if you have a line goes like this, what would be the slope? Positive, right? So that slope and the correlation, right, is at least about the direction of positive and negative. They're related, right? If you have a line fitting this scatter plot that is positive, that means you have a slope that's positive. That means actually the correlation is positive. Okay. So a quick review of why we're doing this and what are we looking at, right, when we have scatter plot. We look at the form of this correlation, right? It is a straight line relation or a non-straight line relation, or there's no even any pattern. We also look at the direction. Is it positive or negative? Okay, and also like to look at the strength. If the strength of the correlation is high, then you will see all these dots will cluster closer together, right? And the relation more like a straight line, right? Or those scattered dots, right, form more like a straight line. Okay, and also outliers. Sometimes they may be a data point here or there. A lot of times those outliers is where the problem is also, right? And you don't want to miss those information. Sometimes those outliers are error. When you do scatter plot, you can find those out and re-investigate on these numbers and determine whether they're really error or really significant information in there. Okay, so outliers are another thing that we like to look at. As I say, if you look at a scatter plot, if all these dots cluster so close together on a straight line, all right, then it means you have a stronger correlation. So this one have a stronger linear relation than the other one. Also, if you look at the pattern of these scatter plot, if the scatter plot look like this, usually we call it, if the trend goes like this, we say there's a positive correlation. Right? If the trend goes like this, as the X increase, as the number of handgun increase, the number of people got killed decrease, right? Then that's a negative correlation. If you can't really find that trend, generally it means there's a really weak correlation that you couldn't tell the trend, right? But sometimes you may have a trend like this that's not linear, but it's very close trend, right? A very clear trend. That means trends still exist, okay? However, later on we're going to learn a number that helps us understand the correlation, and that number actually have trouble to determine whether you have this strong nonlinear trend or not, right? This number is called Pearson sample correlation. Okay, the formula looks kind of complicated, but what it has done is you standardize this xi and yi, right? If you go back to the slide that we had earlier, what is xi and yi? These are xi and yi. Okay, I is a subscript indicating the case, right? I1 probably means the first one. I2 means I equal to 2 means second case. I3 means I equal to 3 means the third case, and so forth. I is an indicator, right, indicating which case it is. So x1, y1 is this first pair. x2, y2 is this second pair. And when I say xi's, that means what? All the x's, all the value for the predictor variable. When I say yi's, that means all those values, right, for the response variable. Okay. If you look at this formula, how do you calculate the correlation? Basically, what you do is standardize for each pair of number, right? For the first number was 447 and then 13, right? So for the 447, you find the standard score of that 447 among all those x's, okay? And then for the first pair of number, for the y, you find the standard score of that y value among all those y values. Okay, I also use a z, xi, and zy. Just stands for the standard score of those pairs of number. What we do is, for each pairs of number, we find their standard score, and we find their product, right? And then we add all those products up, and then divide by n minus 1. That's how we calculate the so-called Pearson's correlation. Okay, I hope this makes sense to you. There is another sheets here that hopefully can help you understand that. And what it does is, if you have mean, right, for the x value and mean for y value, and I'm going to use an example here. If you look at this particular data value, this data value for x, its x coordinate is smaller than this mean value of the overall x value. So because it's on the left of mean of x value. If you look at this value, its y coordinate is less than this 29.43. This was actually if you remember, 447 and 13, right? Its x value is less than mean, y value is less than mean. And if you go back to this formula here, what are we doing in this formula? We're trying to find the product of the two standard score of the x and y, okay, and add all these products. So it's accumulating product of a standard score of x and y. So if we accumulate standard score for this value, x and y, for this point, it'll be negative because x is a negative number. Y is standard score of y will be a negative number. I wonder if I'm making sense. Right? When you calculate standard score, you will have to use the value subtract mean. That's a negative number. And then divide by standard deviation is negative. Right? For y coordinate, if you minus mean of the y is negative, divide by standard deviation is negative. So all these numbers, in fact, if you find their standard score, they will be negative. I'm sorry, negative and negative will be positive, right? Two values are positive. And all these scores over here, if you find their standard score for those pairs of number and multiply them together, they will be all positive. So if you have scatter plot look like this, and you try to accumulate those product of standard score, you'll find out that most of those product of standard score is positive. And if you add them together, that R number, of course, will be most likely positive. What I'm trying to say is, if you do have scatter plot look like this, that R formula, the Pearson's correlation, will more likely be a positive number, right? If instead all these scatter plot, those dots scatter like this pattern, right, mostly in this quadrant and this quadrant, then if you calculated all these z-score, you always will have one that is positive, one is negative, right? So if you try to accumulate those product of z-score, you tend to get negative. So the correlation, Pearson's correlation number will be negative. Okay. I wonder if that makes sense to you, right? But hopefully, this chart actually hopefully can help you to understand how do you calculate the Pearson's correlation, right? Again, I have all these x values here, all these y values here. What I do is calculate the mean of x value and mean and standard deviation of those x value, and the mean of the y value and standard deviation of those y values. Then what I did is, for each of those x value, I standardize it. I use this this value subtract its mean for x, right? Divide by standard deviation for x, for these x's, right? I get a negative 1.31. And I use 13 to subtract the mean of those y. This 13 is y coordinate or y value for this first pair, right? Use the 13, subtract the mean, and divide by standard deviation for all these y values. I get a negative number that is negative 1.35. And then what I do is what? Multiply these two numbers to get this. This is what we call the product of the two standard score of those x and y's. Okay. For calculating the sample correlation, what we do is find out those standard scores for all those x and y's and find their product and add all these products together. Okay? And that is really just doing this, adding those product of standard score together. And the result divided by n minus 1. Okay? So if you look at this, actually the actual calculation for those two z-score, this one is actually 447, the x value of the first pair, subtract their mean, right, and divide its standard deviation, 91.91. That's how I get negative 1.31, and that's this number. Same way we do it for y value, okay? And we find the product and add all these products together. We get 12.24. Divide this 12.24 by sample size minus 1. Totally, there are 14 pieces of data. Divide by 14 minus 1. That's how I get this 0.94147 and something. That is called Pearson's sample correlation. Okay. The computation is a little bit tedious, right? You have to calculate all these z-scores. It's a little bit hard. So when we do a test, right, I think you worry about the test. If we do the test, I won't ask you to do this, but it will be good that you practice this, right, to see how you do this. Right? But I'd like you to know the meaning of this number and how do you interpret this number if people or computer software can calculate this for you. Okay. This number is always between -1 and +1. Okay. And what it does, it measures the strength and the direction of the straight line relation between two variables. Okay, this number is somehow like slope, right? Its sign is like somehow like the sign of a slope or a straight line. If this number is negative, that means you have a negative trend, negative relation, right? So if you have a scatter plot, the scatter plot would go from the upper left-hand corner down to the lower right-hand corner if you look at the scatter plot. Right? If this number is very close to +1 or is positive, then the trend will be like the example that we just seen. Right? All these dots will be scattered like from the lower left-hand corner to upper right-hand corner. Okay. And if all these dots are very clustered, so close together on a straight line, right, then this R value will be very close to 1 or -1. Okay. So if this R value is very close to -1 or +1, that means there's a very strong straight line relation. Okay. Does it make sense? Okay. Hopefully you can interpret this number. And if it's negative, that means you have a negative correlation, right? If it's positive, that means there's a positive correlation. What if this number is 1? If the number is 1, that means all the dots are right on a straight line. Okay, all the dots are on a straight line, not scattered around the straight line. Generally, that's not going to happen when you're doing statistical analysis. And there's a Greek letter rho to denote the population correlation, right? If I do have population of all those pairs of numbers, right, then the correlation for this population of those pairs of number between those two variables, notation-wise, we use Greek letter rho. Okay. Now, there is one thing that you need to be careful. Once you found that strong correlation between two variables, that doesn't mean one variable causes the other. It only means that there's a very strong correlation. Right? It depends on how the data is collected. If the data is collected under a carefully designed experiment, right, try to eliminate possible confounding factor there, right, then maybe you can draw a causal relation between the two. For example, the example that we just saw there, number of handgun registered and number of people got killed. Okay, now we see a strong correlation there, but that doesn't mean that because of so many handgun registered, so there are so many people got killed. Okay, it could be the other way around. Because so many people got killed, so that more people want to buy handguns, right? So maybe that's the correlation is the reverse. Not really, maybe the response is really the factor, right? When you're modeling that. So you can only say that there's strong correlation. You don't want to draw a causal relation, right? Conclusion on causal relation between the two. That's very important. I may give you a multiple choice question and ask you that, right? Or maybe ask you to explain that. Okay. Now, you look at this chart. This is actually about mortality index versus average temperature. Okay, I think we saw this. And this trend is what, positive or negative? There's a positive correlation, right? As the average temperature get higher and higher, the mortality index, this is for breast cancer, yeah, get higher and higher. Does it mean that temperature causing people to have higher risk to get breast cancer? No. These are from several countries there, and it happened that just those countries that have higher temperature, they are more likely or underdeveloped. So their medical facility is not good, okay? And that could be the reason. It's not because of the temperature. Okay? If they have better medical facility, then the mortality rate may go down. Okay? So again, this is an example telling you correlation doesn't imply causation. Okay? So hopefully that makes sense to you. In fact, for this study, the correlation is 0.924. It's pretty high. Okay? And how do they calculate? Just like the formula that I explained to you. Okay? If you look at this one, what's a correlation? Is correlation negative or positive? Negative. Is there a linear correlation there? Yes. The correlation is somehow like straight line pattern. Okay? And what is this? This is a birth rate versus female life expectancy. This is showing that when the birth rate gets higher and higher, the female life expectancy gets lower and lower. And this is data from many countries, 122 countries. Again, you cannot say that because of the high birth rate, right, so that you have low female life expectancy. So you're not going to encourage give birth, right? That's not right, because these countries that have high birth rate, they probably just the underdeveloped. Their education is not giving good education for children and doesn't have better medical care and something like that facility. So that make the female life expectancy lower, right? It's not because of the giving birth to too many kids, not because of the birth rate, right? So you did observe that significant trend, but that doesn't mean one affect the other, right? Causes the other. But there is really a significant trend. So what's so good about this then? Well, if you do have that significant trend, then we can fit a mathematical model to do prediction. So if one country whose birth rate is about 30, then you can predict that, well, the outcome, the life expectancy in this range, right? Now, if these dots get around, like follow a normal pattern, then the mean will be somewhere over here. So you can, well, on average, right, we expect that, well, the female life expectancy about 70, okay? With that trend, you can make that kind of comment, right, for estimation, right, or prediction. Okay. Statistically, actually, we can do some testing for testing whether there is a correlation between variables or not, using that Pearson's correlation. Okay. And when you do that, will set null hypothesis and alternative hypothesis. Your null hypothesis will be there is no correlation between the two. Again, here is a quantitative variable. Right? Female life expectancy is quantitative variable. Birth rate is quantitative variable. And because of those quantitative variables, you can draw a scatter plot. Okay? And that correlation coefficient is for measure the correlation, linear correlation between two quantitative variables. And we can study whether there's a correlation between two quantitative variables or not by using that R, that Pearson's correlation. And usual hypothesis of interest in testing that correlation is that null hypothesis, there is no statistical correlation between the two variables. That means what? That correlation is about 0. That's your null hypothesis. Okay? And the alternative is that there is a statistical significant correlation between the two quantitative variables. That will be the two hypotheses. There's no right side or left side of test. That's it. Unless you're really interested in right side and left side. But most of the time, people just do this. Right? Null hypothesis, no correlation. Alternative, that there's a correlation. And SPS can do this computation of correlation between two variables very quickly for you. Okay? In fact, if you go to our course website in WebCT, right, there's a video, SPS video, on how to calculate the correlation. I'd like you to go home and view it. Okay? And there's an assignment there, if you check on WebCT, that asks you to do this. Right? And answer some questions. Okay? But anyway, if you are able to do that, how do you interpret this table? Look at here. This is female life expectancy and birth rate. This is also female life expectancy and birth rate. Okay. This number here is a correlation between female life expectancy versus female life expectancy. You're talking about variable versus the self, so correlation is 100%. So this is not really what we're interested in. And generally, this thing on the diagonal, this diagonal is not anything that we're interested in. Is the off diagonal, this number. This is a correlation between birth rate and life expectancy, and that correlation, right? You see Pearson's correlation, and this row, the information here, -0.87. That's the correlation. So there's a correlation, negative correlation between birth rate and female life expectancy, and that number is negative 0.87. And underneath that is a p-value, two-sided test p-value. P-value is 0.000. Now, can you tell me, with this p-value, do you reject the null hypothesis? Yes, right? P-value less than level of significance. I didn't say level of significance, but if I say level of significance is at the 5%, this one is less than 5%. So you reject the null hypothesis. What does that mean? That means there is a null hypothesis rejected. That means there is a significant correlation, right? The correlation is significantly different from 0. Okay, and so in fact, most of the time when you run this in most of the software, they also will give you some notation and then put a note here telling you, well, for this particular number with that p-value, how significant it is. Look at here. It says correlation is significant at 0.01 level, right? Which means what? This p-value is actually even less than 0.01. Okay. Sometimes you may see people put a note and put a note here and say correlation is significant at 0.05 level. That means what? Just telling you that, well, the p-value for this test, a test for 0 correlation, is less than 0.01. Right? Here is 0.01. Okay. Does it make sense? Okay. So go to the video clip, right, and view how to do this. It's pretty simple, right? Once you have the data set up, pretty simple. Now let's look at this chart. On top, I have 4 correlation number calculated there, and those are the number calculated from these 4 charts, 4 sets of data. Okay, this first set of data, if you draw the scatter plot, it looks like this. Second charts of data look like this. They have a lot of dots scattered here, but there are 2 dots over here. Okay. Third one, this trend is like this. The fourth one it goes like this, and then it turns a little bit. Okay. If I ask you to do the matching, which one goes with chart A? Chart A has negative or positive correlation. Negative. And does it have a strong correlation? Yes, right. They're all very close to that line, right? So if that's the case, which one will be the R1? That's right, right? And when there are approaches to +1 or -1, generally it means there's a strong correlation. Okay, strong linear correlation, straight line correlation. How about chart B? B matched with what number? R2, right? First, it's positive correlation. Then all these data are so clustered so close together, right? That form a straight line. So R2 is, how about C? Okay. C is a little bit hard, right? We don't know whether, the problem really because of these 2 outliers. And we don't know whether they're correct. They may be correct, but if they're correct, well, is the trend goes like this or like this? It's really hard to tell. Okay. If you look at a D, D goes like this. What would be its correlation? Positive and negative? Positive, right? So I'm gonna, if I do a multiple choice, I may do a little bit guessing. I check this and find out, wow, this is positive. Then this got to be negative because that's the only choice. Okay. But hopefully this helps you to understand when you have few outliers there, that's going to affect the correlation number, right, significantly. Okay. So you need to be careful. Now, do you have any questions so far? Does this make sense to you? How about this one? Do you know how to interpret this? Okay. This number, you see, this box is on this column and this row. This column is for birth rate. This row is for female life expectancy. The top number here is the Pearson's correlation. You get a negative 0.87. So you don't have to worry about computing, getting the standard score and find the product and sum and all, right? If you have SPSS, it can be calculated so quickly for you. And that's the R, negative 0.87. And that tells you that there's negative correlation. Then you go down to the next, that's a p-value, a two-tailed test for this 0 correlation. If this p-value is so small, that means what? Smaller than the level of significance for the test. That means you're going to reject the null hypothesis. Rejecting null hypothesis means rejecting no correlation. That means there is a correlation. Right? But in fact, when you look at this correlation coefficient, you know that correlation is negative. So you can also conclude that there is a strong linear negative correlation between the two variables. Okay? Does it make sense? Any question? Okay, now this is an interesting question, and this comes to modeling, right? Earlier, before this, we just talk about whether there's correlation, right? But once you found the strong correlation, a lot of times people start doing modeling, right, or prediction or estimation. Okay, if you look at this chart here, this is actually the data collected from Yellowstone, right? The geysers, right? They model the eruption of geyser. And anybody went visit Yellowstone ever? No. Okay. There's a geyser there, and then there is actually like a station next to it, and it posts a time. How long should you wait until you see a next eruption? So you can actually go to other places, right, and see other places, and then come back, and then observe that amazing, a geyser eruption, right? But how did they make that suggestion then? The scientists realized that they actually record these eruption, duration of eruption. Okay, when the geysers start erupting, a lot of time it lasts maybe 1 minute, 2 minutes, just keep going, right? But there's a correlation between duration of eruption and inter-eruption time. What is inter-eruption time? After you observe an eruption, then you have to wait until the next eruption. How long does it wait, right? Do you have to wait until the next eruption? So scientists actually, or park rangers, right? They record these information. When they observe a duration of eruption, they record that time, and then also record inter-eruption time, right? How long it takes until the next eruption. And they realize the pattern is very linear. Okay, there's a clear trend. In fact, there are two clusters. There's a cluster over here. There's a cluster over here. They realize that actually you will have a longer eruption, and then after that you have a shorter eruption, and then you have a longer eruption, and then you have a shorter eruption. They've realized that pattern. But from this chart, you actually see correlation between duration of eruption and inter-eruption time. What this can do to help us, actually it can help us to recommend to visitors, right? When you saw an eruption, when should you come back again? Okay? Now, let's say if you observe a duration of eruption is 4 minutes, then how long should you wait until, or do you have to wait until next eruption? Well, you look at the duration inter-eruption time. When the duration of eruption is 4 minutes, the inter-eruption time is scattered from like maybe 65 to 90. Okay? Sometimes 65, sometimes 90. Okay, but it's scattered around that. In fact, if you look at the eruption in that particular time interval, and it follows somehow like a normal distribution. Most of them are over here, but you see some scatter here and some scatter there. Okay, so if you're a park ranger, you want to recommend to people how long should you wait until you see a next eruption? After observe 4 minutes eruption, you probably want to tell people, well, you should come back probably around 70 minutes after. Okay. Then you will see you have a good chance to see the eruption, next eruption. Am I making sense? Okay. So if you have a 5 minutes duration of eruption, what will you recommend to people? Well, maybe like about 80 minutes, right? You should come 80 minutes after that eruption that I observed. If you see an eruption duration that is 5 minutes. Okay. And in fact, mathematically, if you look at these charts, scatter plot, mathematically you can actually find a line that describes that pattern. Okay, and the patterns look like this. And with that model, actually, you can do some prediction. But actually, this line actually goes through. We hope that it goes through the mean, right, average inter-eruption time through all these different range of duration of eruption. Okay. And how do we come up with that line? In fact, if we can come up with that line, right, life will be easier. You can actually use that line and fit in some mathematical formula. So whatever time you're talking about duration, right, you can calculate some formula to help people to estimate how long should you wait at least, right, so that you will definitely see a high chance to see an eruption, right, when you come back. Okay, and how do we do that then? Before we do that, let's review these two variables. Okay, we believe that duration of eruption affects the inter-eruption time, right? So the duration of eruption will be what? Something you use to predict, right, the next eruption. So that will be actually explanatory variable, or factor variable, or predictor, right? The inter-eruption time will be the response variable, outcome variable, because you observe such a long duration, so you got to wait for this long, okay? So inter-eruption time becomes the response variable. I hope this is another good example showing you, right, how to identify your response variable and the predictor variable. Okay, let's go back to the same question that we look at, right? In this case, we know that what is our response, what is explanatory variable. If we try to use a number of handgun register to predict how many people got killed, okay, if that's the case, if you do reverse, you believe the number of people got killed that affect number of handgun register, then number of people killed will be the predictor variable, right? But here, our assumption is that number of people got killed is affected by the number of handgun register. So number of people got killed is the response variable, right? Number of handgun register is a predictor variable. So if we have this set, we can build a straight model, mathematical model that fit this data, okay? So the next time if you have a number of handgun register, you can use this line as a reference line to actually predict, at least on average, how many people will be killed, okay? And how do we come up with this straight line then? Well, straight line formula is like this, right? Y is equal to some y-intercept plus slope times x variable, if you remember, okay? This is called slope-intercept form. A is intercept, okay? Now, if we have a straight line written in slope-intercept form, if we know what is A and what is B, then we have a specific straight line there, okay? All these straight lines are different because of the A and B are different. If you have different A value and B, y-intercept and slope, then you have different straight line. Okay. How do we come up with that straight line if we have a data? In fact, there are formulas that we can use to figure out these two numbers. People call it least square methods, right? To find the best number for A and B so that you can find the line that best describes the relation between the two variables based on the data you have there. Okay. So we want to find a mathematical model to describe the relation between and best fit these data, right? To describe the relation between the number of handgun register and number of people got killed. We got to know what is our A and B. Okay. How do we determine is A and B? I said there's so-called least square principle. And let's not worry about it. But the idea is to find an A and B so that the difference or the distance, right, from all these dots, accumulated distance for all these dots, right, from the line is minimized. Right? That line will be the best line. And with that principle, people can come up with the estimation for A and B. Right? And what are those numbers then? The formula is this. For B, for the slope, it is the correlation, remember the Pearson's correlation, times the standard error for those y's over standard error for those x's, right? All the value for the response variable, you find a standard deviation. All the value for the predictor variable, all the value for the predictor variable, you find its standard deviation. Ratio of these two standard deviation times the correlation, you get the B. That's a least square estimate, right, for B, for the straight line. And the A will be what? The average of those response variable value minus this B estimated here times the average of the predictor variable values. Okay. So if you know the mean of x and y, also know their standard deviation, right, for x and y, and also know the correlation, then the equation is there. You just plug into this formula, you can find that equation. Okay. Now SPS can do this very quickly for you and give you A and B. Okay. But we just talked about the concept here. Okay. So for this particular case, we know the correlation, we know their mean and standard deviation. What we can do is just use those formula, plug those numbers in. B is the correlation time the SY over SX, right? And you get 0.124862. And A is Y bar minus B times X bar is negative 41.43. Just plug these two numbers for A and B, you get that prediction equation. Okay. Again, these are just application of this formula. You calculate B first using the correlation and the standard deviation for both X variable and Y variable, right? And then calculate A. You do B first and then calculate A. Okay. So you can get these. Now you have this equation, you can do prediction. And the prediction is predicting the a point on that line, right? When you have different x value, you can use that equation to predict the y. But that y is actually usually is the average response, average value for all the possible y at that particular level of x. So if we look at an example, just using the same data, if for 1 year the number of handgun registers is 700,000, right? Those data for number of handgun registration is in thousands, right? So for a certain year, number of handgun registers is 700,000. You want to estimate on average how many people will be killed by handgun. Just plug in 700 for x using that equation. The result is 45.9, about 46. Okay? So you can predict on average how many people will be killed, right, at different level of handgun registration. If we look back to this chart, 700,000 is somewhere here, right? And on that line, 700,000 for the number of people killed is about at that level, okay? And that is about 46. Okay, this line, SPS has drawn that line. I didn't do that, right? SPS can automatically draw that line for you, the line that best fit our data, okay? And what the example I just went through is an example showing you how to find an equation for this straight line. Okay, and this line is the line that best fit this data. Okay, so if you want to find a mathematical formula to describe that relation and later on actually use that line or formula to do prediction, this is the line. Okay, and the equation for that, if you recall, is this. Okay, and how do we get this equation? Again, use this formula here. You need to know the correlation. You need the standard deviation for the x values and y value. Now this formula looks slightly different from what you saw in the Blumen's book, okay? But it's much easier, okay? It's only calculation of each of these if you have the calculator, or I mean the Excel or SPSS. This can be done. Actually, if you have SPSS, all A and B, they all can be calculated this right away immediately. Okay. But hopefully you understand what's the purpose for this. All right? We fit a straight line there. In the future, we don't have to look at that chart. With that straight line, I can do prediction. Okay? If you have a certain year, the number of handgun registers is 300,000, I can do that. However, one thing I have to mention, this model is built based on the data you observe for x value that is for about 440 to 700, maybe within 750. So the model only good when your number of handgun register is in this range. If you have data that's outside of that range, the model may not work well, right? If you don't have any knowledge of for x value that is in this range or in this range, then you should not use this equation, just extrapolate and try to do it. Okay. Here is the example. All right, avoid extrapolation. Right. I may have 5 data points and find out this straight line here. Okay. But then people try to use this straight line, all right, to do model. And if 41 day you have x value over here, and you want to estimate the y value using that straight line, well, it's going to be this high, right? But probably in reality, if you do have data in that range, the data goes like this and not like that. Okay? But I don't have any information for data for x value that is in this range. So I cannot really, just say that, well, if the x value is this far and the y value will be this far. No. But I do have data in this range. All right? So if you do have x value, like number of handgun register in this range, then that formula will be good for estimating the number of people got killed in that range. Am I making sense? Okay. The data we used for number of handgun register was around 400 to 700,000. If you have a million, right, or 2 million handgun register, then this model may not be good. You have to be careful. Okay. That's very important. So, and the technique I mentioned to you just now, show you right, how to come up with that equation. That technique is called regression technique. Okay, that line, sometimes we call that line a regression line. Okay, or that equation y equal to a plus bx, sometimes we call it regression equation. You can use that for prediction. Okay. Any question? Do you have any question? Okay. If not, that's it for today. Right? You look.